In previous lectures, we have dealt with Unit 1, which consists of vectors, ordinary differential equations, and Newton's laws of motion. Now, this is Unit 2 of the Mechanics 1, in which we are going to deal with momentum and energy. Now, let us see there are different laws of the conservation of the momentum and energy which we use for the different calculations of the equations of the motion. Okay, to write the equation of the motion of any particle for or any system of the particles, we use these laws of conservation laws of a momentum and energy. So let us deal with the momentum first. So there are two types of the momentum: linear momentum and angular momentum. So linear momentum is defined as P is equal to mv. So this is a mass and this is a velocity, which we have already seen. If the mass is smaller and velocity is greater, it will create a greater momentum. Or even a mass is greater and velocity is smaller, then also it will create a greater momentum. Okay, now angular momentum is nothing but, so it is defined as L is equal to R cross P. Okay, so this is a linear momentum, and this is the trajectory path or the radius of the trajectory path through which the particle is moving. For example, suppose this is a particle which is moving in a rectilinear motion and it is going from A to B, then it is said to have the linear momentum P is equal to m into v if the mass is m and if it is moving with the velocity v. Okay, so the linear momentum is associated with the rectilinear motion. Okay, when the particle is moving in a straight line, whereas this angular momentum is dealing with the trajectory motion of the particle. If suppose this is a particle and it is moving through some curved path b, okay, so if it is having mass m, linear velocity v, okay, then its angular momentum is defined by L is equal to R cross P. All these are vectors, so this is also a vector quantity. So when a particle is following some trajectory path, so this is a radius of this trajectory path multiplied by this linear momentum is nothing but the angular momentum. So there are certain laws of conservations of the linear momentum and angular momentum which are necessary to calculate the motion of the particle or motion of the system of the particles. Now as we have seen that the mechanics, okay, we are dealing with the mechanics 1. So mechanics means motion of the particle or motion of the system of the particles. Now let us see the motion of the particle first. So I'll write it here. Motion of particle. Now motion of the particle is also of two types. First one is a rectilinear motion and another one is a trajectory motion. Okay, so law of conservation of the linear momentum says that whenever the external force applied on a particle is zero, then linear momentum is conserved. Okay, so law of conservation of the linear momentum says that if the external force applied is zero, then linear momentum is conserved. So as we have already seen that if the particle is moving in a straight line, linear momentum is associated with it. Suppose this is A having mass m and if it is moving with the velocity v, so the momentum is given by P is equal to mv. I'll write it here. So P is equal to mv. Now I know that according to the Newton's second law. So the external force is directly proportional to, or it is equal to dp upon dt. So this is the Newton's second law, which says that rate of change of a momentum is directly proportional to the applied force. Okay, so this is equal to d by dt of, let us put the value of this p as mv, as m is constant, dv by dt will remain, and this is nothing but m into a. So this is one more form of the external force. So this is the statement of the law of conservation of the linear momentum, which says that if the applied external force is equal to 0, then the linear momentum is conserved, means dp by dt is equal to 0, and if the derivative of any term is equal to 0, then that term is constant, which means the momentum is conserved. Similarly, if a particle is following some trajectory path, so the law of conservation of the angular momentum says that if external torque acting on a particle is 0, angular momentum is conserved. Okay, now let us define this L is equal to R cross P, and if I take this dl upon dt, so it will become d by dt of R cross P. So I can take the derivative of the first term, or the first term into the derivative of the second term, plus, so this is the second term into derivative of the first term. So let us keep this term as it is, plus p is nothing but mov into this dr by dt is nothing but v, and we know that the vector product or the cross product of the vector with itself will be equal to 0, so which is nothing but r into dp upon dt, and which we know that dp upon dt is nothing but the force. So this is r cross f, and this dl by dt is nothing but the tau. Okay, so if this tau is equal to 0, then dl upon dt will be also equal to 0, which means that if the torque applied on a particle which is following some trajectory path, then the angular momentum is conserved, as the dl upon dt is equal to 0, as the derivative of some term is 0, then that term is conserved. So these are the laws of conservation of the linear momentum and angular momentum for a single particle.